Okay, so that's the hour. So let's get started. So this is MSE 498. If you're not in this class, we do need all the computers. We are full up. So if you don't mind, we'd ask you to vacate your computer to allow folks in the class to use it. Okay, so let me pass around the sign-up sheet. Okay, and so just to get started, just orient ourselves on the syllabus. And so like we said last week, last Thursday, we were working on our Quantum Espresso project. And so this is now September 30th, Tuesday, and so we're going to embark on the next level of our sort of journey together, which is to leave the electrons behind us and start moving on to classical mechanics and start working with sort of atoms and Newton's equations of motion rather than electronic structure. And then we have some deliverables this week, and so 11:59 p.m. on Thursday, you owe me quiz number 2 and project number 2. And so project 2 is obviously the Quantum Espresso project that you're working on. Quiz 2 is like a 10-minute multiple choice quiz that's available on Compass, just testing your sort of fundamental understanding of some of the theory and the practice of quantum mechanics in the context of DFT. Okay, and so before we get started today, are there any pressing questions on DFT or quantum mechanics before we move on? What was the general opinion? Did people enjoy it? Did people find it difficult, challenging? So hands up if it was something new, first of all. Okay, and keep your hand up if you feel like you learned something. Okay, so that's good. Keep your hand up if you enjoyed learning it. Wow, I think everybody kept their hands up. Okay, very good. So we are interested in your feedback, and so if you have any informal feedback you'd like to give me, that's great. We'll probably have like a mid-semester survey halfway through, so you can tell me how good or terrible a job I'm doing. But anyway, so that's where we are and all that stuff. Okay, so let's move on. So obviously I will be available after class and office hours today if you have any last-minute questions on your project. Okay, so let's start talking about lamps and molecular dynamics. Okay, so module 3, and so module 1 was sort of Bash MATLAB, module 2 was Quantum Espresso DFT, and so module 3 is going to be lamps and molecular dynamics. So, like always, we're going to start with sort of a theory lecture, so we want to convey some sort of basic understanding to you of what the heck you're actually going to do when you run the code, and so it's important to have this sort of baseline fundamental appreciation. Next time we're going to start talking about how you actually run the code, and so on Thursday, and then next week we're actually going to do a walkthrough, so we're going to do a simulation together on these machines. So how many folks are familiar with sort of the basic idea of molecular dynamics? Okay, how many people are familiar with Newton's equations of motion, so F equals ma? Okay, then you're all familiar with molecular dynamics. That's all molecular dynamics is, and so I'm going to try and show that to you today. Okay, so introduction. So let's orient ourselves on our time and length scales. And so up until now, we've been working down here, so sort of length scales of 10 to the minus 12, maybe 10 to the minus 9 if you have a big computer, for sort of femtoseconds. So now we say, okay, we're actually interested in bigger systems. I can't afford to calculate the electronic properties of all my atoms. And so I need to resort to a completely different technique. And so the next step up on the ladder is molecular dynamics. And so it's very accurate and very precise in some regards. We are simulating the positions of all the atoms. But of course, we do make approximations in other regards because we're not directly simulating electrons. And so we need to deal with that. And we'll talk about how we deal with that. And then later on in the course, we're going to start to move up here even further. And we'll get to sort of some of these top-end things towards the end of the course. Okay, so 30,000-foot overview, what is molecular dynamics? And so the way I like to think of it is sort of in 3 different ways. Perhaps the simplest way, and this is sort of a view promulgated by Klaus Schulten, who's a very famous and eminent molecular dynamicist right here in the University of Illinois, is thinking about things as a computational microscope. And so it's almost as if we can build all the laws of physics into our computer, watch the ways the atoms respond and move around and behave, and it's almost like we have a microscope allowing us to see the atomic motions of our system. So maybe that's a nice way of thinking about it. Of course, no real microscope currently exists that allows you to resolve things in such detail, but the principle remains. Another way of thinking about it is an experiment on a computer. And so it's very different from solving an integral or perhaps doing some sort of numerical calculations or some statistical analysis. What we're actually doing is building the laws of physics onto our computer and then watching what the system does. And so in that respect, it's like an experiment. We set up our experiment, we set up the physical laws, we set up the initial state, and then we watch what happens. And typically all the real sort of scientific stuff happens afterwards. It's sort of like a post-mortem. In the same way you would go into the lab, you would mix up some chemicals, watch your reaction happen, take some measurements, and then really the analysis is where all the important stuff happens. So we think about it as an in silico experiment is a nice way of thinking about it. And then perhaps the most sort of simple-minded way of thinking about it is basically just simulating the classical mechanics of atoms. so F equals MA at the atomic scale. And I'll show you why we believe that F equals MA works even down at the atomic scale, when up till now we've really been talking about how we have to worry about quantum effects. So we'll resolve that paradox very shortly. Okay, so that's what it is, and so why is it useful? Well, in some cases, the atomic and the molecular motions are really important. And so imagine you're working for Merck in the Northeast Corridor, and you want to design a brand new drug to bind to a particular cell surface receptor. And so you could do that using a computer. You could perhaps make some predictions for what good drug candidates might be. And so it's really important to see the various atomic positions of the cell receptor and the drug molecule. And so you need that sort of atomistic insight into the molecular structure. And so molecular dynamics can give you that. So there are some very powerful experimental techniques. And if you're in the material science department, you may know Jim Zhou, who's one of the most famous electron microscopists in the world. And so he can do some amazing things with electron microscopes over in the MRL. And these can do really astounding resolution of sort of the atomic position. But what we really lack with current experimental techniques is dynamics. And so we can't follow things dynamically. We can get a nice crystal structure, we can get a nice sort of TEM or SEM, but we can't really follow how the dynamics of the atoms move in time. Molecular dynamics can give you that. We can use in silico experiments, so molecular dynamics, to predict and understand molecular behavior, and so we can make hypotheses, things that seem completely unreasonable in experiments. We could say, what happens to my system if I turn off electrostatics? Or what happens to my system if I make this atom 10 times heavier? And so sometimes those can be useful things to develop sort of fundamental understanding that's simply impossible to do experimentally. And so finally, you can furnish sort of all the classical thermodynamics about any molecular system, which is obviously a complete oversell, because you need to know correct force fields, which we'll discuss, and you need sufficient computational power. But in principle, molecular dynamic simulations can give you basically all the thermodynamics you could ever care to know about something in sort of excruciating atomic detail. Okay, so that's what it's useful for. What do folks actually use it for? So why might you be interested in using this either in academia or industry? So we can use it for materials property prediction. Maybe you have a brand new material that your experimental friend has synthesized in the lab, but it turns out it's very radioactive, and so it's very hard to characterize. So maybe a simple way of characterizing might be to do a computational experiment, which is much safer. You can do it in your pajamas, and you can predict things like bulk modulus, surface tension, flow, gelation. So again, you could do in silico experiments to predict physical quantities. We talked about biomolecular modeling, so docking studies of drugs. You can also do things like protein folding, simulate ion transport through membranes. And so biomolecular dynamics is sort of a big field right now, and University of Illinois is actually one of the big places where that stuff is happening. Okay, so we talked about drug design. You can also do things like high throughput molecular screening. So to go back to the pharmaceutical example, imagine you have this enormous panel of drug candidates, and it's incredibly expensive to test each one in the lab because you need to culture a bunch of cells, you need to see if the drug binds to the cells, you need to do flow cytometry, to do an assay afterwards. It's just very laborious, very time-consuming, very expensive. What if we could do computational screening? So we could do high throughput screening, basically in silico, and we could rule out 90% of the candidates right away. And we say, okay, we don't know whether we're exactly right, but we have pretty good confidence these are going to be good and these are going to be not so good. So if you have finite experimental resources, we would recommend you focus your efforts here. And so very similar to the example I presented, I think, on the first day with Ford Motor Company using computational design to save time and money. You can also save time and money in sort of drug design using molecular dynamics. So is it industrially relevant? So, you're sitting in this class, you're not interested in sort of an academic position, you want to go into industry. Is this going to be useful to you? Absolutely. And so computer power just continues to follow Moore's law. So the just is in brackets because there's some questions about whether this will continue. But nevertheless, computation is becoming cheaper and cheaper every year and more powerful every year. And so Moore's law, Gordon Moore, the founder of Intel, said, computational power sort of doubles every 18 months or something. So the number of transistors you can pack on a chip goes up like exponentially with time. And so because of that, industry is very interested in this because there's massive cost and time savings to be made with very inexpensive computation. And so what's very important is that you need sort of reliable and validated models. And so molecular dynamics is now becoming a sort of standard tool. It's mature enough that we have sort of a good handle on good force fields, good models that we can plug into our system. And so the results that we get are becoming more and more reliable and more validated, meaning that it is actually useful for industry to put this into their development pipeline in order to sort of compress the time to market. And so in the same way, perhaps, the computational fluid dynamics became a sort of off-the-shelf standard tool in industry in the 90s, molecular dynamics is starting to move that way right now. And so it's something that's just another tool in the toolbox to get the job done in an industrial setting. So I couldn't really find any good data or a good way to find data on how molecular dynamics is taking off in industry, but certainly it's very easy to do in academia. So you can just do a Scopus search for the keyword molecular dynamics and see how the number of citations to molecular dynamics came up in sort of abstract titles or keywords as a function of time. And so molecular dynamics wasn't invented until around 1955 or so, and since then it's been taking off exponentially. And so I don't know what this terrible dip was here. I guess maybe this was the rebound that people got too excited and it came back down, and now it's going back up again. So the trend is good. Okay, but nevertheless, there were over 10,000 journal papers published every year with people doing molecular dynamics, and so this is something that everybody does. Okay, so just a brief sort of history, just to orient yourself. Where did molecular dynamics come from? How was it born? So it was first developed by Bernie Alder and his collaborator Wainwright in 1957. And so you may recognize Bernie Alder's name from the local density approximation. The paper was by Sepperly and Alder when we were talking about DST exchange correlation functionals. And so Bernie Alder was also involved in the birth of molecular dynamics. So a very eminent guy. He's currently an emeritus professor at UC Davis and received the Boltzmann Medal and the National Medal of Science. Super famous scientist. And so the first simulation that was ever done was molecular dynamics of a hard sphere fluid. And so a complete synthetic system. It's just like billiard balls moving around in a box, but it provided proof of principle that one could, in principle, simulate the dynamics of atoms on a computer. So really exciting. And so this was the very first simulation over the timeline here in 1957. And since then, it's just sort of exploded. And so 1960 was sort of the first real simulation of copper radiation damage. And people today are still working using molecular dynamics to simulate radiation damage to materials, particularly in nuclear reactors. So Pascal Bellon in this department, material science, works on this sort of thing experimentally and computationally. There's then a simulation of liquid argon, which is typically the first simulation anybody does when they first do a molecular simulation. In the same way that the first code you ever write in Bash is Hello World, the first molecular dynamics simulation you typically do is liquid argon because of this sort of history here. Then we got into slightly more complicated things, and so we started worrying about liquid water, of course very important for biomolecular simulations. And then much of the development over the last few decades has really exploded in biomolecular simulations. And so protein folding has been one of the big drivers of molecular dynamics in the last sort of 30 or 40 years. And so right now there's this chap called David Shaw. Is anyone familiar with the name David Shaw? So he's an investment banker, so D.E. Shaw is a big investment bank. So he's also an adjunct professor at Columbia University, and so he has this beautiful building in sort of Midtown Manhattan. And the bottom, 5 floors are like his hedge fund where he makes gobs and gobs of money, and then the top 5 floors are like his computational molecular dynamics infrastructure, where he basically takes the money from the hedge fund and gives it to all these scientists to do molecular dynamics. He built this enormous machine called Anton running some special software that just goes lightning fast, and he's now been able to simulate a real-sized protein in explicit water for 1 millisecond. And so that's just phenomenal. If you're in the field, you realize what an enormous achievement of this is. And so it's basically like having Blue Waters, the supercomputer on campus, just in your building in Midtown Manhattan, and you can just do these crazy simulations. And it's a really interesting guy. And so he's spending all his hedge fund money to do science, which is kind of cool also. Okay, and so just a sort of brief history. Okay, so let's get into what I actually want to tell you about, so you have some basic appreciation for what we're going to do next week when we do some simulations. And so I think out of all the 4 topics we're going to cover, so doing DST, doing molecular dynamics, doing sort of finite element modeling, and calculation of phase equilibria, perhaps the fundamentals of molecular dynamics is the simplest. So the idea is really very simple. And so we just want to simulate the atomic motions using classical mechanics. And basically running a simulation is like cooking. And so I once saw a talk by Alexey-Mentiev, who's in the physics department here, and he had this beautiful idea about molecular dynamics being like cooking, and I think that's really true. And so just follow the recipe. And so these are the ingredients. What do we need? We need 3 things. An initial system configuration, so just like quantum espresso, you need to tell the computer where your atoms are and what kinds of atoms they are. You then need to tell the computer how the atoms interact, so how they speak to one another via force field. And then you need to tell it how to integrate Newton's equations of motion. If you have those 3 things, you're done. Then you know everything about the system. And so we're going to go through each of these 3 things in a little bit of detail right now. Okay, so let's take one quick detour, two quick detours. First of all, let's go back to Pierre-Simon de Laplace. And so actually in sort of the beginning of the 1800s, he in some ways predicted the advent of molecular dynamics. And so if you're familiar with Laplace's demon or the clockwork universe, basically he said the following. If there was a vast intelligence which could comprehend all the forces of nature, so basically the potential function, so how atoms talk to one another, and the respective positions of the beings which compose it, so basically your initial conditions, so where the atoms live at a particular moment in time. And if you could submit these data to analysis, so integrating force equals mass times acceleration, those are the three ingredients of molecular dynamics, nothing would be uncertain in the future, and the past would be present to its eyes. And so basically we could then integrate Newton's equation of motion forward and backward and see the complete evolution of the universe. And so of course, knowing the quantum uncertainty principle and, finite computation and errors exploding due to numerical round-off and things, this is not completely realizable, but the fundamental idea is true. So this is basically what we're trying to do, and it was predicted by Laplace in the 1800s, which is kind of interesting. Okay, so the second quick feature, what about quantum effects? And so we worried a lot about, quantum mechanics. We had this horrible exchange correlation functional. We said we don't even really know, even today, what's going on under the hood of quantum mechanics. It's very confusing. How can we possibly simulate atomic motions using classical mechanics if we don't have any faith that not representing the electrons is an okay thing to do? Okay, so classical mechanics represent atoms, or sometimes united atoms, which are sort of collapsed atoms together. We'll get to that. As point particles that move deterministically via Newton's equation of motion. Is this okay? Yes. And I'm going to explain to you why we think it's okay. Okay, so the rationale number one, the Born-Oppenheimer approximation allows us to treat the electrons implicitly. They're sort of baked into the nuclear interaction potential. So the idea being that if we look on long enough time scales, the electrons are basically slaves to the motions of the ions. And so the ions are moving around, and at every instant, the electrons are moving so much quicker that they instantaneously equilibrate to the ion position. And so that means if we're only interested on long enough time scales, we can basically bake in the electronic effects to the ways in which the ions interact. So we can have an effective ion interaction potential that takes account of the equilibrium structure of the electrons. And so electrons, a characteristic time scale sort of 10 to the minus 18. Nuclei move on a characteristic time scale of 10 to the minus 15 because they're so much heavier. And so basically there's a separation of timescales argues for this pseudo-equilibrium that allows us to implicitly treat the electrons. So I think this is probably a fairly familiar argument. People have heard of this sort of approximation, separation of timescales type argument. So there's another argument, which you may prefer. You can pick the one you like best, which is basically to say that the Schrodinger equation collapses into Newton's equation if you look on large enough length scales. And so if you compute the de Broglie wavelength, so the quantum wavelength, of a particular atom, and so a hydrogen atom or a carbon atom, you find that for everything but the lightest atom, which is basically hydrogen, the de Broglie wavelength is much, much smaller than the characteristic nuclear separation. And so for hydrogen, it's about 1 angstrom. For carbon and everything heavier, it's some fraction of an angstrom. And so that means if all we're worried about are atomic separations on the order of an angstrom, quantum effects really don't play much of a role, except for the very, very lightest atoms. So basically we have a separation of length scales. And so if we're worried about things on the order of sort of angstroms and bigger, quantum effects don't really come into play too much because they exist at a much smaller scale. And so we do have to do something a little bit special when we simulate very light elements. But for heavier elements, for all intents and purposes, we can forget about quantum effects because that's not the length scale we're interested in. The physics that we're interested in happens in a different place, in basically the classical regime. So thinking about it as a separation of length scales or a separation of time scales, whatever you prefer. So that's the rationale for why molecular dynamics can work. Okay, so are there any questions so far before we get into the three ingredients? Okay, so let's start. So the initial configuration. So that was ingredient number one. We need to know where the atoms are at a particular time. And so we need to specify initial atomic coordinates and velocities. And so, like Pierre-Simon de Laplace said, if we know the initial state and the interaction rules, they fully specify the system's future and the system's past, subject to numerical sort of round-off errors. And so basically, we do have a wind-up universe. And so the problem is that our intelligence is not sufficiently vast, or at least mine isn't, and so we have to use some numerical simulations in order to predict how the system is going to evolve. And so that's why we're actually going to use the computer. because basically it comes down to doing the same thing over and over again, which is integrating Newton's equations of motion, which computers are really great at. So that's why we in fact use more and more powerful computers to do bigger and bigger systems. Okay, so how do you initialize coordinates? So the last slide sort of showed this really nice visual picture, but you know, as you realize, when you do computation, it's all sort of boring text files, and so this is sort of the reality. So the last slide was like the dream, this is the reality. Basically, it's just a text file full of numbers. And so this is a particular protein in water. It specifies the sort of the protein name, and then it gives the 3 Cartesian coordinates at which it exists, and then it gives you the velocities of the atom in those 3 Cartesian coordinates. So super boring, but this is how the computer interprets it. And so for very simple things, maybe you can generate your own initial positions and velocities. Maybe you can just write the file using a text editor. So if you have something like a perfect crystal, you could now you're all experts in Bash, write a very simple Bash script to sort of write a file like this with all the atomic coordinates and velocities. For much more complicated things like proteins or structures with defects or anything that's not sort of very simple and periodic, there are a bunch of tools that you can use. And so I've just listed some of them here. So prod.rg is great for proteins. PyMol is pretty general purpose. And sometimes you can actually just download the structure directly from the internet. And so whenever an X-ray crystallographer discovers the structure of a new protein, typically they upload it to this thing called the protein data bank, and they're obliged to also upload all the coordinates in a sort of standard format. And so folks who want to do molecular simulations can then just go and grab that file, and now they have all the initial coordinates of the protein atom. And so it's sort of one of the most tedious steps in setting up a simulation is getting your initial configuration, but there are lots of tools to help you do it. Okay, so that's coordinates. So how about velocities? And so maybe the simplest thing you would say is, well, why don't we just start our simulation with all the atoms at rest? And so everybody is sort of sitting statically at basically 0 Kelvin. So there's no thermal fluctuations, there's no net flow, everybody's just sitting there very happily. So the problem due to that is once you start doing your simulation, typically you want to do it at finite temperature when actually stuff happens. Absolute zero is not a particularly interesting thing to do molecular simulations at. And so that causes a thermal shock because basically you dump in your initial coordinates, all the atoms are at rest, you start your simulation, the simulation wants to start moving the atoms around, and so there's this massive ramp in temperature which can actually cause your system to destabilize and sort of explode. And so typically that's a very bad idea. And so the simplest solution is to draw velocities randomly from a Maxwell-Boltzmann distribution. And so you may be familiar with this distribution. Basically, you know, if you're not, don't worry about it too much, but it basically is the equilibrium distribution for the velocities of atoms in an ideal gas. And so if you have an ideal gas at sort of 100 Kelvin, the distribution of velocities sort of looks like this. This is just a histogram. These are the molecular speeds. If you have 300 Kelvin, it looks more like this. 1,000 Kelvin, it looks more like this. And basically, you can just use your molecular dynamics engine to sort of sample from this distribution and randomly assign velocities. And so that means that when you start your simulation, it's already at the right temperature, because we all understand that temperature is basically velocities of atoms, it's atomic motion, and so the system is much more stable. And so you never have to do this manually. Typically, there are codes to do this, or actually your molecular dynamics program will do it for you. So you can flip a flag and tell your molecular dynamics software that I'm giving you some atomic coordinates, I'd like you to assign the velocities randomly using this approach. It's just a very standard thing to do. Okay, so that's ingredient 1, coordinates and velocities. So coordinates, you can generate it yourself, download it from the internet. Velocities, typically you draw them from a Maxwell-Boltzmann distribution so you have the right temperature, and your software will typically do that for you. So not too many tricks there. So number 2, interaction potential. So this is the second ingredient. We have our atoms, we know where they are, we know what velocities they have, at least initially. So now we need to know how they talk to one another. If we didn't know how they talk to one another, we would just basically have a boring ideal gas. And so nobody would be interacting with anyone else, we wouldn't have a condensed system, and we wouldn't have life as we know it. And so we need to know how the atoms talk to one another. And so this is known as either a force field or an interaction potential. And so these two words are basically interchangeable. And so basically it tells you what is the energy of atom A given the positions of atoms B, C, D, E, F all the way to infinity. And so if this atom lived here, how does it talk to all of its friends and what energy does it feel? So what's the energy of an atom in the system? And so what's very important in order to have any reasonable results from molecular simulations is you need to trust your force fields. And so they need to be accurate, robust, and transferable. So what does that mean? They need to be accurate in that they give you the right energy. They need to be robust in that if you perturb them, so if you change the temperature or the pressure, you don't want them to go crazy. You want them to still be accurate. And you want them to be transferable. So if you take them from one system to another, you'd like to believe the results. And so the development of really accurate, robust, and transferable force fields is sort of a big industry in academia. And so there are groups all over the world who basically devote a lot of time and energy into developing these good force fields so that folks can do realistic molecular dynamics simulations. And so some of the models that we use are sort of listed down here. We'll talk about them in 1 second. But maybe the way to think about this is that it's sort of garbage in, garbage out. Unless you have a sort of good, reliable force field that you trust, you're not really going to be able to trust any of the predictions of your simulation. So it's really important to have a nice validated force field. So these things can come from actually quantum mechanical calculations. So folks might run things like quantum espresso and use the results from a quantum espresso run to start parameterize a force field. And so in that way, you're baking in the electronic effect. So for example, maybe you would take your hydrogen molecule, you would simulate it at a bunch of different bond lengths, and you would measure the energy quantum mechanically using quantum espresso, and you would then build that into an effective potential that basically just gives you the energy as a function of the bond length. And so that's implicitly capturing all the electronic effects. And so that's something you actually right now have all the tools to do. You would be able to build a force field for the hydrogen molecule. Of course, when you get to bigger systems, things get much more complicated, and so you have to start using some of these guys down here. So for biomolecules, there's a whole bunch of things here. For metals, which is the thing we're going to be considering, the most famous ones and most widely used ones are the EAM and the MEAM potential. So we'll get to that in just 1 second. Yeah, question? They're all freely available typically. So I don't think there are any, to my knowledge, sort of proprietary force fields. So typically these are things that are either built into your molecular dynamics software or you can download the files. Yeah, good question. Okay. So the potential energy of the system, so the force field that gives you the potential energy, is a complicated function of all the atomic coordinates, and so that's why basically we have to simulate things numerically rather than calculate analytically, because these functions are incredibly complicated. And so then it becomes very simple. If you know this and you trust it, the potential energy V as a function of all the atomic coordinates, you just take the gradient, put a negative sign in front, and that gives you the force. And so now we have the force in Newton's force equals ma. And so now we have the force that enables us to numerically integrate, which is the third ingredient. And so acceleration is just force over mass, and that tells you how your atomic velocities and positions are changing as a function of time. So it all boils down to this function v. So it's a very complicated function, and so typically we take a reductive approach, and we build our force field from a number of different components. And so we have the total v out here, and we break it up into a number of contributions. So there are many ways to break it up, but the standard way is to break it into bonded, non-bonded, restraints, and fields. And so I'll show you what each of these little chunks are right now. Okay, so bonded potentials is exactly what it sounds like. If you have two atoms that are bonded together in some way, we need to sort of simulate that. We need to mimic that in our force field. So if you have just a straight up covalent bond, you might mimic that with a sort of harmonic potential. And so maybe this would look something like this. And so you can get this from quantum mechanical calculations or sometimes even from spectroscopic data or things like this. If you have angles, typically you also model that with a harmonic spring, or you have dihedral angles or improper dihedral angles, which are basically these torsional motions. They tend to be modeled with sort of products or sums of sines and cosines. And so a torsional angle potential might look something like this, which says basically I'm really happy if I'm in the trans state. There are a couple of local potential wells corresponding to the gauche state, and then it really doesn't like to be in the eclipse state. And so, you know, just a standard torsional potential. They all typically look something like this. Okay, so non-bonded potentials. So if the atoms are not connected by covalent bonds, how do we simulate things? So typically they interact either by van der Waals or Coulombic forces. And so for van der Waals, this is something that we're all sort of familiar with. So the Lennard-Jones function tells you it looks typically something like this. So it's also known as sort of a 6-12 potential. And so basically, the atoms really don't like being very, very close together because of Pauli exclusion. And so the electrons are occupying the same region of space. They hate that. And so there's some sort of repulsion. There may also be electrostatic repulsion sort of baked in there. But basically, this is Pauli exclusion. And then as you go to some larger separation, the atoms have their equilibrium separation. They're interacting nice and happily because of dispersion forces between the electrons. And as you go out, obviously this has got to decay to infinity, because when they're infinitely separated, there can't be any attraction or repulsion. And so actually this 6 comes from quantum mechanical considerations, that the way the electron clouds oscillate and interact with one another actually gives you this sort of scaling with the separation to the power of 6. Does anyone know where this 12 comes from, this Pauli exclusion 12? So it comes from 2 times 6. So it turns out that all you need is a really sharp slope up here. And so the folks who started developing these force fields said it actually makes the numerics much easier if you have this being sort of just very closely related to this. And so they said, well, let's take 12. And so there's no reason this couldn't actually be 14 or 10 or something like this. And so there's not too much interpretability here. This just gives you the hardcore repulsion that stops your atoms collapsing on top of one another. Okay, and then we have Coulombic attraction. And so I don't think this needs much explanation. Unlike charges are going to attract according to the Coulombic potential energy, which goes like 1 over r, and like charges are going to repel with a repulsive interaction of 1 over r. So super simple. Okay, so that's bonded and non-bonded. So what was this weird one called restraints? And so I said to you that if we have really light atoms like hydrogen or neon, we are not so sure that we can completely forget about quantum mechanical effects. And so we have to worry about that a little bit. And the typical way of sort of fixing this up is to say, okay, I know my light atoms are going to sort of be influenced by quantum mechanics because the de Broglie wavelength is similar to their bond length. But what I'm going to do is I'm going to say that I'm interested in timescales much longer than the fluctuations of that very light atom. So I'm just going to pin the atom in space. I'm just going to say, okay, you're not allowed to fluctuate. I'm going to fix your bond length. So that means forevermore you've just got to sit at your equilibrium separation. So that means I can't trust predictions at timescales shorter than the characteristic oscillation of that bond, but at timescales longer than that, I can say, okay, well, basically the bond length has annealed, it's equilibrated to the rest of the system, and I'm pretty content not to worry about timescales that are very, very short. And so you can basically bootstrap or sort of augment your force field with some restraints to pin these light atoms, so like we said right there. Or you may actually want them to do some sort of funny stuff that you could never do in an experiment, which might be to sort of make atoms rigid or make molecules rigid, and see what influence that has on your system. So for example, perhaps you want to see how the fluctuations of an ion channel affect the sort of ion conduction through it. So you could do a simulation with the ion channel free and fluctuating. You could do a new simulation with the ion channel fixed, and then you could measure the difference in the current. And you could say, actually, the fluctuations are really important, or the fluctuations are not at all important. So you may use your restraints for investigations like that. So the best way to think of it is just a component of a force field, of the force field. And then finally, you may worry about things like fields. And so perhaps you have some external potentials. You might have an external electric field, an external magnetic field, or a net flow in your system. And so you need to build that into your force field. You need to tell all the atoms, hey, you've got to interact with this electric field or this magnetic field, or you've got to have this net flow along the x-axis, for example. Another way we can use fields is, imagine you have a really, really big protein molecule and you want to simulate it in water. Your computer's not big enough to explicitly simulate all the water molecules, so maybe you'd use something called an implicit solvent, which is basically just solving continuum electrostatics. And so you say, actually, I'm not going to simulate every single water molecule. I'm just going to use the sort of field description for the water, and that's going to save me a lot of computational time. And so sometimes we use things called continuum or implicit solvation. And so that's sort of meant to be represented by this sort of cloud, this field contribution to the force field. Okay, so the good news is that you typically never need to worry about picking apart these contributions, but I think it's important for you to understand that there are different contributions to the force field, and typically they're broken up into bonded, non-bonded, restraints, and fields. And so you may play with some of those in your input file when we get to doing our simulation. Okay, so let me just highlight one particular force field, because this is the one we're actually going to be using, and it's the one perhaps most relevant for material scientists, which is this EAM or MEAM potential. And so these stand for the embedded atom model, or the modified embedded atom model, which are basically potentials that we use to simulate metals, and so sort of condensed crystal structures. And so that's in fact what we're going to do to simulate aluminum. And so the sort of potential function looks like this, and so don't be scared of this. Basically all we have is two contributions, and so the total energy comes from a sum of pairwise interactions. So I look at every atom in my crystal, and I ask, how far are you away from all of your friends? and then I use that to compute an interaction energy. Okay, so that seems a reasonable thing to do, all pairwise interactions. And then there's this funny sort of non-local contribution. And so this says, it asks each atom, what is your local electron density that comes from all of your friends all around you? And then it says, well, given that, I know what extra energy to add on to the potential. So it's basically broken down, and this is sort of the take-home for the EAM, into pairwise and sort of an embedding function. That's all I sort of want you to understand there. And so let's dig into the local energy density functions just a little bit, because it distinguishes EAM from MEAM. And so EAM sort of just takes the average density of electrons coming from all the other atoms surrounding your tagged atom. So how much do the electron clouds from all the atom's friends impinge upon it? And that gives you sort of a net electronic density. It turns out that doing this doesn't really work very well for highly structured crystals. So things like BCC, HCP, or diamond structures, this sort of fails pretty badly. And so it turns out you need to augment this with some extra terms. And so instead of just saying, what is my net electronic density, you also need to bootstrap this with some sort of radial and angular terms that says, okay, I'm sitting here, I know my net electronic density, but I also know that there is one of my friends sitting up here, one of my friends sitting down here, and one of my friends sitting down here. And so you actually get the directions and the locations of your nearest neighbors, and that allows you to make a more powerful force field that can actually simulate these more complex crystal structures. So this is our first choice of potential if you're doing a simulation of a crystal. It's typically EAM, but if you have a sort of more complicated crystal structure, you may need to use something like MEAM. And so that's all I want to say there. Difference being, this has some sort of angular terms in it. Okay, so the good news is you can just download these all for free from this, and so this goes back to the previous question. These are all online. And actually, as part of your project, you're going to be going to this website and downloading a MEAM, I think. Yeah, I think we're going to use a MEAM potential for aluminum. Okay, so that was the second ingredient, so force fields. So any questions about that? Okay, so ingredient number 3, integrators. Okay, and so we have the locations and the velocities of all our atoms. We know how they talk to one another, and so we can take the gradient of the potential energy, put a negative sign in front, and that gives us a force. And so now we have their acceleration. And so now, like Laplace would say, we have all the information we need to predict the entire future and the past of the system. And so how are we going to do that? We're going to simulate by numerically integrating force equals mass times acceleration. Okay, so we can't do this analytically, so it turns out if you have more than a two-body system, you can't actually solve this analytically, so that's why we're going to use computers. In principle, we could do it by hand, but it's going to be extremely painful, so let's not do that. And so this is really the reason we have molecular dynamics software. If we could solve it analytically in the same way as if we could solve the Schrodinger equation analytically, we wouldn't need any computational material science software, and I would be out of a job. And so fortunately, that's not the case, and so we need to use simulation. So I think it's always important to have appreciation of, why are you simulating? So anybody can run a molecular dynamics code. Not anybody can tell you the fundamental ideas or explain to you, why you actually need the simulator in the first place. And so it's important to have an appreciation of why you're doing what you're doing. Okay, so there are many possible integration algorithms. And so are folks familiar with sort of the Euler algorithm for numerical integration? So just super simple Taylor approximation. In your numerical analysis classes, you may have seen some fancier things like Gear predictor corrector or Runge-Kutta. The good news is for molecular simulations, we actually use almost the simplest possible numerical integration algorithm you can think of. And it goes by the name the Verlet algorithm. And so I think every single molecular dynamics software package you would ever encounter uses the Verlet algorithm. And so we'll discuss that in the next slide. But why do we use Verlet? It's super simple, it's very fast, it's low memory, stable, and then the funny thing that you may not have thought about before is that it's time reversible and symplexic. So these things are all good from a computational and a programming standpoint. This is really the big reason that we use it. And so Newton's equations of motion are time reversible. So like Laplace said, we can integrate the future, we can integrate the past. And so it turns out the Verlet algorithm preserves that time reversibility. So if you integrate forwards or backwards, it looks the same. So in principle, you could start your system from time 0, integrate to t equals 1, and then integrate back to t equals 0, and you would get the same initial state that you started with using the Verlet. It turns out some of these fancier integration algorithms do not preserve this reversibility. And so it means if you simulated to t equals 1, and then reversed your algorithm and simulated backwards, you would get a different initial state. And it turns out that's bad. The reason it's bad is that it causes massive errors to start accumulating in your numerical simulation. And so you might think it would be good to use a more complex algorithm because it allows you to get greater accuracy and do bigger time steps, but it turns out that in the long run, it's a bad idea. So the errors in each single time step can be improved by going to a more complex algorithm, but the errors in the long run are going to kill you. And so what we need is a very simple algorithm that has a good error, a good error in the long run, that we don't want to be accumulating horrible numerical errors in our very, very long molecular simulation. So it's a little bit subtle, but basically if you can understand that it's very simple and that it's time reversible, that's probably good enough. Okay, and so it turns out that the Verlet algorithm was actually also came from like the beginning of the 1800s. Actually, end of the 1700s. It was first discovered by D'Alembert, and then it was popularized by the chap whose name goes with it, Luc Verlet, in 1967. So again, molecular dynamics was anticipated way back in the 1800s. It just turned out because we needed computers, you know, that's the only reason we had to wait a few hundred years. Okay. Okay, so what is the Verlet algorithm? So I'm putting this slide up even though I don't like to sort of expose you to too much math, but because it is so simple. And so basically we take a Taylor expansion forwards. So the position of your atom at t plus delta t is your position of your atom at time t, plus its velocity times delta t, plus 1/2 times its acceleration times delta t squared. So this is just a vanilla Taylor expansion, nothing fancy here. Going forwards in time. So velocity, acceleration. You can also do a Taylor expansion backwards in time. And so your position at t minus delta t is your position at t minus your velocity times delta t plus, because this is squared, your acceleration times delta t squared. So that gives you a backwards Taylor expansion. So if you just used one of these, your error would basically go like delta t squared. But it turns out if you're smart and you take these two guys together, you can subtract one from the other, and you can actually get a delta t to the fourth error. And so your error is actually really, really small. And so this is the Verlet algorithm. Why is it the Verlet algorithm? Because it tells you, if you know your acceleration, how to update your positions, and if you know your positions, how to update your velocity. And so this is what is happening under the hood of your molecular dynamics simulator. It's taking the current positions and velocities of your atoms, and it's updating it according to this rule. And so this tells you immediately you're not going to be able to take an infinitely large time step because you need to take your time step sufficiently small that your error is controlled. And so this is why molecular dynamics simulations take a long time, because each time step has got to be sufficiently small that we don't make a horrible error. So typically these time steps are on the order of about a femtosecond. And so if you want to simulate a nanosecond, that's going to take you a long time. And so femtosecond to nanosecond, you need to do sort of millions of steps. And so that's why we can't just immediately, you know, make the time step as big as we want. Okay, so I'm never going to ask you about the math, but I think it's important to sort of have it. So again, like the quantum espresso theory, you should view these lecture notes as sort of like a library, just a place you can look to try and understand what's happening under your simulation. I don't think it's any use to sort of memorize these things. Okay, so one last thing about the Verlet algorithm. Like we said, higher order integration algorithms have higher per step accuracy, but in the long term, you're going to get horrible error accumulation, basically because they're not time reversible. And so I'm just trying to illustrate this here with this nice plot. And so what I'm showing you here are three integration algorithms and the error that they make as a function of time. And so leapfrog is basically just another name for Verlet. And so you can see that over the long run, the Verlet error is pretty much flat and sort of not doing too badly, even at very long simulation times. Whereas the error in Runge-Kutta fourth order and the midpoint algorithm sort of go crazy. And so if we were to use these, we might be happy doing a very short simulation with them, but in the long run, our errors are so bad that we can't really believe the results. Okay, so that's enough on the Verlet. Very simple, but very powerful algorithm. Okay, so any questions on that? Okay, so let me first head off any worries you might have due to numerical errors. And so there's a sort of famous molecular simulation book called Frankel and Smith. So if ever you do molecular simulations, typically the first thing you do is read this book. And there's a beautiful sort of couple paragraphs in there which refers to this as the skeleton in the closet of molecular dynamics. And so it's sort of the bugbear that underlies molecular dynamics that people worry about, and this is why we shouldn't worry about it. Okay, so what is the skeleton in the closet? The skeleton in the closet is So whatever integrator we use, we're going to introduce numerical errors. So we have finite precision on our machines, so we're always going to have some sort of error due to truncation and round off. So if you're perhaps thinking about Laplace saying you can integrate the entire future and past of the universe, and it occurs to you, well, what if you start to accumulate errors? I've heard somewhere that classical mechanical systems can be chaotic, and so that's true. So chaotic in the strict math sense of a sensitive dependence on initial conditions. Doesn't that mean that if I make round-off errors, we're going to actually perturb our system in such a way that we're going to accumulate sort of errors exponentially because they're going to explode. They're going to go crazy because of this chaos. And so that is true. And so this means that two simulation trajectories produced by two different machines could actually diverge exponentially in time. And so you start up a simulation on your EWS machine right here. You go for a coffee, you come back, you get some results. You go home, you start the same simulation on your laptop at home, you run it, you go and get a coffee, you come back, and actually the results are different. And so they could be different because of this chaos property of the Newton's equations of motion. That you could actually get this very sensitive dependence on the initial conditions, and the way your machine rounds off or truncates the numbers could lead to this divergence. So how can we possibly trust molecular dynamics simulations if we don't even get the same answers from two different machines due to this sort of chaotic explosion of errors? So here's the answer. Okay, there's first a very sort of esoteric answer, and then there's sort of the practical answer. So the esoteric answer is something called a shadow orbit. So again, this is probably the least important slide I'm going to present to you today, so don't worry about it too much. But basically, it turns out that if you use a symplectic integrator, which basically means one that's time reversible like the Verlet, it may not conserve the true Hamiltonian of the system, so the true potential function of the system, but it actually conserves one that is very, very close to it. So you have your potential function that you believe the system is evolving according to. It doesn't quite because of this chaos property, but it does evolve to one that's very, very closely related. And so the numerical errors plus your potential function basically give you this very closely related potential function, which your system does perfectly evolve according to. So there's no chaotic craziness in that particular potential function. So the bottom line is that simulation trajectories do not diverge too far from the true trajectory. So that tells us we know we're going to get these problems due to the chaotic explosion of errors, but we know in a strict mathematical sense that they are going to be controlled. And so we're not just going to diverge crazily. Okay, the more practical answer is that typically we do not care about a single molecular dynamics simulation. So you do one simulation of a defect hopping in aluminum. How do we know that that trajectory is actually representative of anything? And so in a real chunk of aluminum, there's going to be Avogadro's number of defect hops sort of in a laboratory time scale. And so typically what we want to do is run a bunch of molecular dynamics simulations and take an average. And so in that sense, because we're averaging over several simulations, we're not worried too much about divergence because our mean is going to pull us back to sort of a reasonable answer. So this is the sort of mathematical interpretation of why we're not worried. This is sort of the practical interpretation. So it always gives me pause whenever I read in the literature that somebody did this heroic millisecond simulation of a protein, but did it only once because it was so expensive you couldn't afford to do it more than once. You know, how do we know how representative that trajectory is? Would it be more useful to perhaps do 5 or 200 shorter simulations and take the average? There's always a trade-off. Okay, so that's the skeleton in the closet. Okay, so we talked about the three ingredients, and so let me just sort of compress this together in a couple of slides, and actually a little movie in a second. And so we arrive next week. We want to start a molecular dynamics simulation. What do we do? Okay, this is us arriving next Tuesday. We sit down at our machines. We then initialize the positions and the velocities. So ingredient number 1. We calculate the forces for all molecules using the potential, or atoms if we're doing an atomic system. That's ingredient number 2. That was our force field. So you're telling molecular dynamics code, hey, I want you to use this force field. You then do some funny business, which we'll talk about later, which might be sort of controlling temperature, controlling pressure, controlling tension. So some extra stuff that you might want to tell your simulation to do. We'll talk about that later. And then this is ingredient number 3. So you use your Verlet algorithm to update the positions and the velocities. And so like we said, we can't just take giant time steps. We can't integrate from t equals 0 to t equals 1 nanosecond because our error is like delta t to the 4. And so we have to take a bunch of very, very short time steps. So we'll typically do femtosecond time steps. So 10 to the minus 15. Okay, so then we repeat this, so we integrate round and round and round this loop, and then we get our results, and so we've now conducted our in silico experiment, and then we do a post-mortem. And so we have how our atoms move over the entire nanosecond simulation trajectory, then we analyze it. So we can ask the simulation to give us all the thermodynamic properties, we can ask it to give us all the dynamic properties that the atoms experience as they're moving around, and we can actually draw some scientific conclusions. Okay, so to perhaps show this a little more graphically, this is sort of a nice slide. So we start up our simulation, atoms have positions and velocities. We tag each atom in turn, ask how it interacts with all of its neighbors. We then compute the net force on the atom. So we remember the Newton's equation of motion don't care about where the forces came from, they just care about the net force on the atom. So basically we sum up all of the forces it experiences. These could be bonded, non-bonded, restraints, fields, all the stuff that went into the force field. We have a net force. We do that for all the atoms, and then we integrate. So we update the velocity according to the Verlet algorithm, we update the positions according to the Verlet algorithm, and then we're back to the beginning. And so this is the super repetitive inner loop that takes all the time in your molecular simulation. So once you've set up the system, once you've given it all the information it needs, you just press go, and this is the time where you go for a coffee. Okay, so any questions on anything so far? Okay, so let me show you a nice movie. So I think the sound is working, which sort of puts a lot of these things together. Okay, let me start that again so we get the beginning.
Partial charges are then calculated by some form of quantum method to represent the distribution of electronic charge on those molecules. For a polar molecule like water, these partial charges can actually be quite large, with the best part of a full negative charge on the oxygen atom. In molecular dynamics, bonds typically represented as simple harmonic oscillators, as are the angular constraints. To start the simulation, a range of velocities is chosen that matches the Boltzmann distribution all at temperature, and then those velocities are assigned randomly to each atom. Similar methods are then used to put energy into the bonds, angles, and daisy tools. The simulation is then run according to the Euclidean physics, with the molecules transferring both energy and momentum to one another via electrostatics and plasma valves interactions. So in these simulations, water is essentially a hard sphere with 3-point charges. Surprisingly, such a simple method for modeling this gives surprisingly good results on numerous physical properties that can be calculated. Maybe the best of these is the structure. So we plot the average probability of finding oxygen in a unit volume with distance out from a specific water molecule, we get what we would call a radial distribution function. Now, it turns out these structural functions can actually be measured directly by our experimental methods such as neutron scattering. Essentially, these very simple methods do an okay job of modeling the structure of water. Now, we've not.
Okay, so that one's, you can look at the movie online if you're interested. It's a little bit longer than that. But basically, just give you an appreciation. This is obviously very water-centric, and what we're going to be doing is sort of very metal-centric. But the idea remains the same. So sort of encapsulating the ideas that we can simulate Newton's equation of motion. This is the first time I've presented to you sort of comparisons to experimental data. So hopefully you appreciate that actually we can do a pretty good job of predicting things that are physically relevant. Question? How many runs? How many separate runs? So typically you can start doing it in 2 ways. If you're simulating at equilibrium, you could just do one ginormous long run, which is basically the same as doing a bunch of short runs. And so you could either do one sort of 100 nanosecond run, and then you could average over the whole thing, and then maybe you could do some block averaging. Then you could take the first 10 nanoseconds, compute the mean, the second 10 nanoseconds, compute the mean, the third 10 nanoseconds, compute the mean, and that might give you some error bars. Alternatively, you could actually do 10 distinct runs, and that can be useful because you can run them all at the same time, and so you can parallelize your runs, and that would give you the same result. So that's at equilibrium. If you're looking at non-equilibrium phenomena, so you're waiting for a rare event to happen, there are a lot of tricks that one has to do, and we'll discuss some of them. But basically, in that case, maybe the characteristic timescale for a process to happen is on the order of tens of nanoseconds, so perhaps for a defect to jump, in which case, in the simplest sense, you might just need to wait tens of nanoseconds in order to ever see this thing happen. So the answer to your question really depends on what you're trying to study and what your understanding of the system is. That's the idea. So yeah, so they were running a simulation, and so I guess you saw the curve started off really wiggly, and then it sort of flattened out. And so they were basically simulating long enough such that their properties no longer changed in time. And so then you can say, okay, I seem to have reached equilibrium, and so I've reached a steady state. So that's one good test for whether you know you've simulated long enough or not. You need to see if your properties are no longer dependent on how long your run is. Yeah, good question. Yeah. Yeah, that's a great question. So yes, so if you're simulating something, the characteristic time scale is sort of several microseconds or something, what can you do? So you can't study it using standard molecular dynamics, but a huge industry is accelerated molecular dynamics. And so there are a number of really smart techniques based on some pretty beautiful sort of statistical thermodynamics as to how you can use molecular dynamics to capture rare events. So how do you simulate things at long time scales? And so I think we'll talk about that very shortly, actually. Yeah, good question. Yeah, so I guess the way to boil that down might be, okay, your characteristic time scale is limited to a femtosecond because that's your integration time step. So what do you do if the event you're interested in has a time scale of nanoseconds or microseconds? So yeah, we'll come to that very shortly. Okay, so that's the basics of simulation. So if you understand sort of everything up to now, you have a general appreciation of what we're talking about. Basically, you understand the fundamentals of molecular dynamics. So if you can remember those three ingredients and remember sort of something that I told you about each of those three ingredients, you're probably in reasonable shape. So now we're going to talk about things that are a little more advanced. And so typically, you need to know a little bit more than what we've just discussed in order to get some reasonable simulations of sort of interesting systems. Okay, and so the first thing we were talking about was constraints, and so we talked about this as a component of the force field that sometimes you might want to restrain or constrain atoms, and so this is digging into this a little bit more deeply. So the idea that bonds and bends of light atoms might be temporarily decoupled from the rest of the system, and so you might want to sort of pin these and sort of at their equilibrium position, so you no longer update them with time. And so the way you know whether you can pin something or not, so whether you can constrain something or not, is to look at the characteristic time scale. And so light atom bond stretches and bends all have time scales of sort of 10 to the minus 14. So provided you're interested, seconds obviously, so provided you're interested on events longer than that, sort of going towards picoseconds or nanoseconds, you can sort of constrain these things and not worry too much about them. So this is why these are in red. So typically we always constrain these things. These motions, so global DNA twisting or subgroup motions, have longer time scales, so 10 to the minus 12, 10 to the minus 7. So typically we can't pin those things, and these time scales are even longer. And so depending on what time scale you're interested in, that might allow you to accelerate your simulation by constraining certain parts of it to their equilibrium bond lengths. So the principle in action here is very similar to the idea of pseudopotentials in quantum mechanics. So we applied a pseudopotential to our system because we said we don't care about the core electrons. We know that all the action is in the valence electron, so let's save ourselves some computational cycles by using a pseudopotential. Same idea here. If we don't care about the things that are happening on really, really short time scales, let's save ourselves some CPU cycles by just pinning those to their equilibrium lengths and worrying about things that are happening on longer time scales. So similar principle. And there are special algorithms that we use to enforce these. So it turns out that the first one was called SHAKE, and this was some acronym. Because these things are always developed by computer nerds, they love puns, and so the next one that came out was called RATTLE, and then the last one was ROLL. So hilarious, I know. And there are others called LINX and SETTLE. And so typically, if you want to constrain stuff in your system, you just tell your molecular dynamics code, hey, I want to constrain this, and I want you to use one of these algorithms, and it does it for you. It modifies the way the Verlet algorithm updates Newton's equation of motion to respect the fact there are hard constraints in your system. Okay, so that's maybe a minor point. A very important point is the ensemble. Okay, so has anyone taken sort of a statistical thermodynamics class or any sort of thermodynamics? Okay, so some folks. So you'll probably be very familiar with this. For folks that haven't seen this before, the idea is very easy. So molecular dynamics occurs in something called the NVE ensemble, which basically means that you have a fixed number of atoms, and you have a fixed volume, and you have a fixed energy. So when we start up our system, we give the atoms some initial energy through their velocities. We specify the number of atoms, and we specify the volume in which they live. And then when we run the simulation, those things don't change. So we don't lose atoms or gain atoms. We can't gain or destroy energy, and we don't change the volume of the space in which the atoms live. So that's standard molecular dynamics. So it turns out that your friend down the hallway who's actually working in a laboratory doesn't operate in the NVE ensemble. They're doing experiments typically in the NPT ensemble. So they don't have a fixed volume and a fixed energy. Typically they have a fixed temperature and a fixed pressure. So that's what we talk about standard laboratory conditions, sort of 298 K in 1 bar. So how can we convince our molecular dynamics simulation in this ensemble to, instead of having a fixed volume, have a fixed pressure? So that means the volume of the system might have to change. And instead of having a fixed energy, have a fixed temperature. So that means that the energy of the system might have to change. We might have to couple it to a heat bath. So the simple idea is that molecular dynamics is most simply formulated in the NVE ensemble, but typically we want to get results in usually the NPT ensemble. So that's just the idea. How do we thermostat and barostat our system such that we're simulating at sort of laboratory conditions? Is that sort of clear to everyone why we'd want to do that? Okay. So usually molecular dynamics is restricted to fixed N, but we're not restricted to fixed V and E. So how might we change that? So basically we need to add a thermostat and a barostat. So the temperature of a system is defined as the average atomic velocity. And so just by sort of equipartition theorem, so standard statistical thermodynamics, the kinetic energy of the system is just summing up the kinetic energy of all the constituent atoms. So a very easy thing to do in a molecular simulation because we know all the atomic velocities. And then we just use this formula, which don't worry about it, it just comes from statistical thermodynamics, that we have our kinetic energy on the right-hand side, we have this crazy expression on the left-hand side, but basically you can find the temperature by dividing your kinetic energy by 1/2 times the number of degrees of freedom times Boltzmann's constant. So it's a simple calculation. This happens under the hood in your molecular dynamics simulation. So at every time step, your molecular integrator computes all the velocities, then the software computes the kinetic energy, and then it tells you the temperature. And so if your atoms are moving really fast, you're going to have a high temperature. If your atoms are moving really slow, you're going to have a low temperature. And so how do we control the temperature? We rescale the velocity. So it's a very simple thing to do. So usually we have sort of conserved energy, but then we add this extra bit onto our integrator and say, okay, I'm actually going to add a thermostat. So I'm going to figure out what the temperature of the system is at a particular instant, and it might be sort of 320 Kelvin. And then I say, well, actually I'm interested in 298 Kelvin. So I'm going to need to change the velocities of all the atoms. And so you just rescale the velocities until you get the temperature you're interested in. It's a very easy calculation. It's very easy to implement in a molecular dynamics package. There are a whole bunch of ways of doing it. So I'm just providing, again, thinking of these slides as sort of a library for your own information. These are the different algorithms one can use to do thermostating. But basically what it boils down to is in your molecular dynamics input script, you just flip a switch, you flip a flag that says, I want you to use a thermostat. It's really simple. So at every stage in our molecular integration, we have Verlet algorithm, then this extra thermostating algorithm, basically. Okay. So we can do a very similar thing for the barostat. So we set up our atoms, we put them in a box with a certain volume, and then we say, okay, I don't actually want to simulate a fixed volume, I want to simulate a fixed pressure. So how do we do that? Through a barostat. So it turns out the way you compute pressure is in the following way. It's the kinetic energy minus this thing called the virial. Don't worry about this, it's just some crazy expression that's this tensor product between the atomic positions and their forces. If you're interested, I can tell you where to find out more about this. But again, it's a calculation that can happen very easily in your molecular simulation. You know all the positions, you know all the forces, you can make this product, and you can plug it into this expression and get the pressure. And so at every step, again, you compute the pressure according to this expression. Maybe it's 14 bar. It turns out you're interested in simulating at 1 bar. And so you're going to have to change the volume of your box in order to get it to the pressure that you're interested in. So we do that through a barostat. We're changing this quantity in order to make this the value that we want. And so again, a couple of different algorithms to do that. So if we attach a barostat to our simulation as we run through the numerical integrator, we do Verlet to update the positions and the velocities of the atoms. We do a thermostat to update the temperature to be what we want. And we do a barostat to update the pressure to be what we want. And so, very simple. It's just adding extra steps to our numerical integration at every step. Okay, so much for thermostats and barostats. So that's great. That means we can now simulate in the NPT ensemble, so fixed pressure and temperature, meaning that our results are directly applicable to things that our friend down the hallway might find in their experimental lab. Okay, so the next sort of more advanced topic is periodic boundary conditions. So we have a problem if we're simulating on a sort of finite-sized computer, meaning sort of any computer, in that we don't have infinite memory. So we can't simulate an infinite system. We have to simulate a finite-sized system. So very similar to quantum espresso, when we were using that, we defined a sort of fundamental simulation cell, and so we're simulating a small patch of space. So that's fine. So maybe you want to simulate a small patch of space in which your molecules are existing. However, if we want our simulation to actually mimic a bulk system, we need to do periodic replication of that cell. So imagine the thing I want to simulate is a ginormous box of water. So if I were to just simulate a small, sort of nanoscopically sized box of water that fits on my computer, the molecules would feel the walls of the box very strongly because it's such a small box that the molecules are really interacting more with the walls than they are with one another. And so the way that you trick the system into believing that it's living in an infinite bulk phase is to use periodic boundary conditions. So folks heard of periodic boundaries before? So it's a pretty simple concept, but it's very powerful. And so this is our fundamental simulation cell. So this is the thing we actually simulate on our computer. This is our volume, and these are our atoms, A and B. But instead of telling the atoms they're living in a box, we tell them they're living in a periodically replicated grid of these cells. And so we have a cell that lives here that looks identical to this one. So it's got atom A here and atom B here. We have a cell here that looks identical. Atom A and B, atom A and B, atom A and B. And then obviously in the third dimension, we would replicate it in and out of the board. And so this doesn't cost any extra computational power because these guys are just replicas of this one. So we don't have to do anything extra. We get them for free. But the important thing is that now we have periodic boundaries. So what does that mean? It means that if atom A gets very close to the wall and sort of moves out here, it flips back in the other side. And so it's like it tunnels back in through the other wall. And so if A sort of moves here, it moves here, it actually reappears on the other side of the box. So it's a periodic boundary. It's as if I walked out that door and came in back in this one. And so if any of you saw like one of the Matrix films, like Keanu Reeves is in this like subway and he's been like trapped there or something, he like runs out one subway tunnel and comes back in the other side so he can't escape. It's basically that. It's a periodic boundary. Okay, so why is that important? Well, it means that A no longer realizes there's a wall here because it just comes back in the other side. And so we've obviously got to update all the other boxes as well. And so A moves up into here. So that means it moves up into here. So that means it moves up into here. And so all the other periodic images also get updated. So why is this important? It means we can sort of trick the system into thinking it's living in an infinite bulk phase without any walls on a finite-sized computational machine. Okay, so I'm trying to illustrate this again right here. And so you can see these sort of atoms moving around. And so if this guy moves down through the floor, he comes in through the ceiling. This guy moves sort of in through this wall, he goes out through this wall. And so we're tricking the system into thinking it's infinite. So the first time you hear this, it sounds really, really weird. But basically it's a very simple concept. And actually you might see it in action in some of your visualizations in the work we do next week. Okay, so is that sort of clear to everyone? Okay. So attendant to periodic boundary conditions is something called the minimum image convention. And so we have a problem. If we have periodic boundaries, it means that a particle could see multiple copies of itself because it's been periodically replicated. So imagine I just gave you this central box. So what is the distance between particles 1 and 2? So you would say this. So this is the distance between particles 1 and 2. It turns out that's not the distance between particle 1 and 2 when you use periodic boundary conditions, because particle 2 is actually very close to particle 1 if it's able to look through the periodic wall. And so particle 1 can look all around it. There's a whole bunch of copies of particle 2 because we've replicated the cell infinitely in every direction. And so it turns out the one that you're interested in is the closest one. And so you just have to be aware that when you're computing distances in this sort of weird universe with periodic boundary conditions, you need to worry about that you could have a closer image through the wall. And so that immediately means that we have to make sure the distance at which particles are allowed to interact with one another cannot be greater than half the size of the simulation box, because then they could see multiple copies of their friends, and that would just cause all sorts of non-physical results to happen. So we only want particle 1 to see one copy of particle 2, and that means that the distance it can look out into space, so the sort of range of the interaction potential, has to be sufficiently short that it only sees this guy. It does not see this guy, this guy, this guy, this guy. So that's just a concern we have to worry about. And it turns out if you try and run your molecular simulation input file and you have an interaction distance between for your force field that's bigger than half of your box length, the program's going to complain. It's going to tell you that, no, you can't do that. It's going to cause all sorts of problems. So please either increase your box size or reduce your interaction range. So don't worry too much about this formula. This is just the way you calculate it. But we need to make sure that our cutoff distance is smaller than half our box length. And so the cutoff is the distance, the maximum distance at which particles can interact with one another. Okay. Any questions about periodic boundary conditions or minimum images? So it's not something you have to worry about every day, but if your code breaks, you need to know that this might be the reason it breaks. And so, if you're running your code and you get this weird error that says, your cutoff is greater than half your box length, if I hadn't shown you this slide, you would have no idea what I was talking about. And so this is the idea of prepping you with the fundamentals to actually do some practice. Okay, so then I think this is the last advanced. Yeah, so okay. So we want to talk about long-range electrostatics. So van der Waals interactions decay like 1 over r to the 6th. So we saw that in an earlier slide. Coulomb interactions decay like 1 over r. And so they're very, very long ranged. And so it means that they decay really, really slowly. And this actually causes big problems into enumerating things. So the long-range nature of Coulombic interactions meant that there was actually, in sort of the 50 years folks were working with molecular dynamics, there was not a good, fast algorithm to rigorously treat Coulombic interactions. This was a huge problem until around 1999. It's actually a very recent past. Only then was there a fast enough algorithm to properly treat electrostatics, which led in part to the explosion in all the simulations that you see, that curve of the trend in molecular simulations. It allowed us to properly treat Coulombic forces and really do better simulations than could ever have been done before. And so this is just illustrating the sort of die-off of Leonard-Jones, r to the 6th, versus Coulomb, 1 over r. And so we need to worry about really, really long things, which cause a lot of problems numerically. So it turned out there was a very smart way to do this. And so it turned out there's this thing called the Ewald algorithm, or Ewald summation, which is a very elegant technique to rigorously treat long-range electrostatics. If that's the only thing you remember, that's fine. So just remember you can rigorously treat it using this thing called Ewald summation. Just to provide you a little bit of history and a little bit more understanding, Paul Peter Ewald developed this algorithm, and so it basically does a really smart thing. And so it says, this is what my system looks like. So these are my point charges. This is a plus charge, a minus charge, a plus charge, and the interactions are really, really long-ranged. It decays like 1 over r. So Ewald then said, well, actually, there's a smart thing you can do. Let's pair up each charge with a Gaussian of the opposite sign and the same net charge. So we shield this positive charge with a negative Gaussian, so smeared out negative charge. We shield this negative charge with a smeared out positive charge. We shield this positive charge with a smeared out negative charge. So that means that at very long distances, this actually looks like it has no net charge because this plus cancels this minus. Similarly, at very long separations, this plus cancels this minus, and this looks like it has no net charge. So it means that when you have two of these guys, these shielded charges separated at a very long distance, you actually don't need to worry about their interaction. And so it means that the Coulombic interaction of this combined system converges very fast. So what have we done? We've taken our system of plus and minus charges, which we didn't like very much because we need to worry about 1 over r decay, and we hid this minus charge in a plus cloud. And we hid this plus charge in a minus cloud. So that means if they're far enough apart, these two guys don't really interact because they're net neutral. Okay, so that sounds good, but now we've screwed up our system by adding these clouds. So now we have to subtract off the impact of these clouds. And he said, well, okay, we can do that, because it turns out that if you subtract off the effect of these clouds, there's a plus sign because he slipped all of the clouds. So this cloud we added here is flipped up to the top line here. You can actually treat this very efficiently using Fourier transforms, because this basically just looks like a bunch of sine waves or cosine waves stuck together. And so in the same way as we treated the K-space in quantum espresso, it's a very similar technique right here that we can subtract off the impact of how we screwed up our system very efficiently in Fourier space. And by adding these two contributions together, we get our original system with high accuracy. So that's the rudiments of the Ewald method. So level 1 of understanding, there is a fast method to treat electrostatics called the Ewald method because the interaction decays like 1 over r. Next level of understanding, this is actually how it works. Third level of understanding, this is what Ewald looks like. Okay. Okay, so that's all I want to say about Ewald. All right, so I think that will do it for today, actually. So we have a couple more advanced techniques to talk about. And then next time we'll finish up that. We'll watch a couple of movies of molecular simulations in action. And then we'll have about 10 slides and actually the praxis of molecular simulation using labs. And that will do it for Thursdays. And then next week we'll actually do some simulations ourselves. Okay, so that's it for today. So I'll stick around in case you have any questions about this or about the project. And do remember, project is due on Thursday, 11:59 p.m. along with the quiz. Okay, sounds good. Thanks, folks.